Hello all. I will be briefing about CE 421A Professional Elective 5. It is 2 plus 1 3 credit course. 2 credits are allotted for theory, 1 credit is allotted for lab. We will have 3 lectures per week and we will have 1 lab session per week. To brief you about the course, let us consider a simple example of simply supported beam loaded with UDL of intensity W1 over its partial span, and on partial span it is loaded with triangular load with highest intensity W2 as shown. Let us say the beam has length L and flexural rigidity EI. Let us say this figure depicts the deflected shape of this beam. At distance x from left end, we have y directional deflection as y. So how many numbers do we have in our hand? So x can vary between 0 to L, and for every x we will be interested in finding out y. So theoretically we have infinite number of unknowns. The same problem I can look at it in a different way. Let me split this beam into finite number of elements shown as E1, E2, E3, E4, E5 and E6 here. And I will consider the y directional displacement and start and end of each element as unknown. So therefore the number of unknowns now I have in my hand are y1, y2, y3, y4, y5, y6, y7, that is total 7 unknowns. By doing so, I have converted infinite number of unknowns into finite number of unknowns. Within the element, I can assume the y directional displacement to vary as say linear, quadratic, cubic or any other degree function. So let us say we assume the linearity. So therefore within the element the displacement varies from y1 to y2 as a linear function of x, y2 to y3 as a linear function of x, and so on and so forth. The shape that I have drawn in red color here, therefore, gives you the approximate deflected shape obtained by converting infinite number of unknowns into finite number of unknowns. You will agree with me that as number of elements increase, the size of elements goes on shrinking, and in the limit, as the size of element tends to 0, this approximate deformed shape will overlap with the exact deformed shape which is marked in blue line here. So therefore this strategy of converting infinite number of unknowns into finite number of unknowns by discretizing the continuum into the finite number of elements and then treating only the displacements at start and end of the elements as unknowns is termed as finite element method. There are certain crucial questions. What should be the optimum element size? What should be the degree of interpolation function? Should it be the linear interpolation as shown here? Should it be quadratic? Should it be cubic? So on and so forth. These questions will be answered in this course. Now, where is the applicability of this finite element method? So as you can see, and as you must have experienced, most of the problems in civil engineering domain can be represented mathematically as differential equations. So wherever you are in a position to express the problem as a differential equation, the finite element strategy can help you in solving that problem numerically. What are the prerequisites of this course? So the prerequisites are differentiation and integration and stiffness matrix method. So if you are well aware about these two things, then you will be able to grasp this course pretty quickly. This course is mathematical in nature, so we will have to solve a lot of problems. Very less theory is involved in the discourses. So you have a problem solving attitude. You must have a problem solving attitude if you want to learn this course. So with this introduction, let me stop here. The syllabus I believe has already been shared with you. If not, please contact me on my WhatsApp number. I will share the syllabus with you. Thank you.